Cosmology and Gravity Laboratory is part of the Institute for Fundamental Study, where we conduct research in theoretical physics concerning gravity and the history of the universe. Our group is organised around three core members, Dr. Kampi Karwan, Dr. Pitayut Wongjun, and Dr. Tirapab Chantavat, and two associate members, Associate Professor Buring Gunjuppai and Dr. Matthew James Lake. Various topics in cosmology and gravity are studied in our group. One of the main areas of research in our group are studies to explain the accelerating expansion of the universe, for example, dark energy and modified gravity models.
Observational evidence suggests us that the universe expands accelerantly nowadays. So theoretical physicists try to expand this observational evidence. There are many kinds of theoretical models from now. Nowadays we can classify many models into two classes. First is a kind of model which adds an exotic matter field into the right-hand side of Einstein field equations. We call this kind of model is dark energy because we don't know what dark energy is nowadays. The kind of dark energy model depends on the matter field we added. The simple model of dark energy model is just add the most simple field, which is scalar field, into Einstein field equations. We call this kind of model quintessence. The more complicated models also investigate. For example, vector field model, we add vector field into the right-hand side of Einstein equations. One of the most important theoretical model is just two-form field, which is the area subject we're working now also. Another kind of model, there are many kinds. For example, Chapin gas or holographic dark energy model. So I move to another class of the model which just try to modify gravity itself instead of put an exotic matter into Einstein field equations. In other words, just modify the left-hand side of Einstein field equation. We call this kind of model is modified gravity model. There are also many kinds of modified gravity model. The most simple is just put any functions of Ricci scalar instead of Ricci scalar itself into Einstein-Hilbert action. And we call this is FR gravity model. Another model is just FT gravity models or any kinds of modified general relativity. And one of interesting model we are working now is massive gravity theory. In this theory, we just put mass term in Einstein-Hilbert actions and try to explain this mass as a cosmological constant to drive accelerated expansions of the universe. They also have another kind of model which working on theory in higher dimensional space-time. We call one of example of this kind of model is Benver model. Now, theoretical physicists try to explain the observational evidence by constructing consistent theoretical model.
Another interesting research topic is the inflationary model, a rapid expansion of the early universe believed to have happened shortly after the Big Bang.
To solve some problems in the hot Big Bang universe, we propose that the universe expand with the acceleration during the early epoch. A possible model for the accelerating universe in the early epoch is called inflationary models. In our group, we investigate various inflationary models using the cosmological perturbation theory to compute the observable quantities, and using the theory of reheat and preheating to study particle creation after inflation.
Or even the study of the large-scale structure of the universe, where various sets of observational data are taken into account.
When we actually test the cosmology, we're talking about the object on a very large scale. Okay, That's what we call the large-scale structure of the universe. And there are two aspects of this kind of structure. First is that if we look at the universe at a particular time, okay, at a single redshift, you can see that we get information by what we see that the object that distributed on the sky in the same redshift doesn't actually distribute it randomly. There is some correlation between those objects. Another aspect is we look at the observation at different redshift. This is to test the evolution equation of the universe, and if we combine those data together, we can actually tighten the constraint on the parameter or the theory. Observation is, in my opinion, it would be as important as theory, because without observation in cosmology, okay, we would not be able to test whether the theory of the structure formation or modified gravity is actually works. And actually there are two ways that we can test the theory. The first one is to do the observation, and the other one is to run an embodied simulation in a computer. And this era would be an exciting time for cosmologists because they back at about 20 or 30 years before. Cosmology is like in the realm of theories because there was no observation whatsoever to test the theory, but at the moment we have a lot of telescope and the technology that is strong enough to actually see the object at a very high redshift, and we have telescope that has very high resolution to actually distinguish the object at high redshift. And even the first light that happened during the Big Bang era, the cosmic microwave background.
Cosmological perturbation theory that describes the evolution of the universe.
In the standard notion, the structures in the present universe, such as stars, galaxies, clusters of galaxies, etc., are developed from the small perturbation around homogeneous and isotopic spectrum in the early universe. An important tool for investigating nature of the perturbation in the universe is the theory of cosmological perturbation. In our group, we use the cosmological perturbation theory to study physical properties of many cosmological models, and we also study some features in the cosmological perturbation theories.
Or mysterious objects such as black holes.
General relativity is theory that describes relation between space-time curvature and matter field. The most important in this theory is Einstein field equation. This equation is highly nonlinear coupled differential equation, so it is not easy to solve these equations. One have to impose some symmetry into the theory to find the solution. The first solution found by Schwarzschild, he imposed spherical symmetry into the theory. And the most important thing in this solution is that there exists coordinate singularity at specific radius, which even light cannot be escaped. So it means that we can observe anything in this radius. So we call this solution is black hole solution. And there are some evidence, observational evidence that indicate that there exists the black hole in the real world. So people try to study Einstein solution in spherical symmetry. Namely, we can add charge into these equations. We call this solution is linear non-stop. Or we can study the rotating solution, which is we call curved black hole. There are many kinds of solutions. One of important thing of the black hole solution is that they have a black hole law, which is equivalent to thermodynamic laws. And people try to understand this kind of equivalence. This is one of research area. Another research area is just try to find particle motions or effects of objects around the black hole. Also, we can treat the black hole as a quantum object. So the black hole is not really black. They have some radiating from quantum effects. So some of theoretical physicists try to find some gravity factor to describe property of the black hole. Also, as I said before, they have a kind of modified gravity. So try to find black hole solution in modified gravity theory is one of the research area.
Our research group has many research collaborations with foreign experts. The Institut d'Astrophysique de Paris, or IAP, with Professor Benjamin Vandelt. Jamia Malia Islamir with Professor Sushant Ghosh. Our RGJ scholarship students will be co-supervised by Professor Bin Wang from Shanghai Jiao Tong University, China. Other research collaborations. Our laboratory is funded by many grants, both internal and external. The research funding from the Thailand Research Fund, the Torre Research Grant, the Naresuan University Grant, Thailand Excellence Centre in Physics Grant. The laboratory funding is allocated to research students within the group. All of our graduate students are fully funded to cover academic fees. Our academic staff are willing to help and consult with the students at any time. Our institute has a pleasing teaching and research atmosphere. Our goal is to develop our research to an international standard. We would like to encourage our young generation to develop their scientific potential to the fullest. And we are proud of being able to help train knowledgeable theoretical physicists in Thailand.